Good morning. I'm Rekha Thomas, and I'm here to introduce our first plenary speaker, Pablo Parrilo. Pablo is the Keithley Professor of Electrical Engineering and Computer Science at MIT, and he holds a joint position in mathematics there as well. He received his undergraduate degree in electronics engineering from the University of Buenos Aires in 1994, and a PhD from Caltech in control and dynamical systems in 2000. Pablo is a world expert in many aspects of optimization and control theory, and he has a very special focus and many contributions to algebraic methods in these fields, especially polynomials, sums of squares, and so on. His contributions have been honored with many prizes. He's won the Ekman Award from the American Automatic Control Council, the SIAM Activity Group in Control and Systems Theories Prize, the Farkas Prize from the Informs Optimization Society, and an invited talk at the International Congress of Mathematicians in 2010. He's also a fellow of IEEE and SIAM, and please join me in welcoming Pablo Parrilo.
Hello. Does this work? Okay, great. Thank you for the invitation. Thanks for the introduction. It's really a pleasure and an honor to be here. In particular, of course, I want to thank Sandra, Caroline, and Jan, who were the ones making sure that I do everything on time. And let me jump in directly to what the talk is going to be about. So before I say this, everything that I say is joint work with a wonderful subset of people. Amirali, Jason, Raphael, and Benoit. And let me motivate this directly from some considerations in optimization, right? And one of the things that we know is that trying to understand algorithms, trying to understand the behavior of algorithms is really about trying to understand the behavior of dynamical systems, different kinds of dynamical systems. So let me do perhaps what the simplest case of optimization, which is we're trying to optimize a simple quadratic function using, for instance, some gradient descent algorithm. Right, so one typically writes some kind of descent method of this type, where this is simple iteration that I go from my current point to the next point by moving in the direction of the gradient. And in the particular case, for instance, when I have, again, a quadratic function, really understanding the behavior of this optimization method is really understanding the behavior of a linear recursion, right, the linear differential recursion, difference equation. So the question that I'm interested in, or the question that I'm going to use to motivate somehow this is what happens when you switch between algorithms. And what I'll try to point out, at least just at the beginning with a simple example, is that interesting things actually can happen, because essentially when you switch between different things, somehow unexpected things may occur. And what I want you to imagine is, for instance, what would happen, as I said, there's many algorithms for optimization. Gradient descent is just one of them. But what would happen if I take one step of gradient descent and one step of something else, one step of something else? I mean, can we expect these kind of things to actually work? And for this, let me perhaps give like a simple example, just to try to understand that surprising things happen when you start switching between things, really the miracle of non-commutativity. So let me take this matrix, for instance, A, some constant matrix. Let me take B, some other constant matrix. And let me make the observation that if I form an infinite product of all the matrices A, then the norm of the limit of the norms of the product is 0, both in the case of A and in the case of B. And this is, of course, true, because in particular, A and B are nilpotent. So I don't even need to take, in this case, infinite products. Just taking two products is kind of enough for the matrix to be 0. Right? But notice, on the other hand, that if I start switching, if I apply first A, then B, A, B, then actually the norm of this matrix goes to infinity. Right? So somehow, again, it's like a perhaps non-trivial observation that, here, one of the matrices, their powers go to 0, the other one powers go to 0, but when you mix them, something different happens. Now, of course, every time that something like this happens, you should think this is an opportunity, let's say, for instance, for designing algorithms. Right? So perhaps you can actually do this in reverse. You take an algorithm which is slow, or you take an algorithm which is bad, perhaps it doesn't even converge. And if you want to think about switching perhaps between those, right? And perhaps you can obtain a better algorithm or a faster algorithm. And there's many variations. Of course, at this level, everything is kind of a little bit too general. But let me just give a particular example where these kind of things actually can give you something quite productive, and then we'll talk a little bit about the mathematics of it. Right, so as I said before, the simplest thing in optimization is minimizing a quadratic function. Typically, the assumption that we make is if you minimize a complex function is that you have some upper and lower bounds on the eigenvalues of the matrix. Essentially, it's an upper and lower bound on the curvature of this quadratic function. And just for concreteness, let me pick little m to be 1 and big M equal to 5. Doesn't really matter. Right? So as I said, the basic method is to really do the gradient descent. So that takes exactly the form that I talked about before. We have a linear iteration that depends, of course, on the step size, what step size I use. And of course, there's some kind of trade-off in there between doing very small step sizes where you do very little progress at every iteration versus taking big step sizes that perhaps may lead you to something non-converging. It's kind of well known that there's an optimal step size choice that one can write explicitly in terms of little m and big M. It turns out to be this 2 over little m plus big M. Again, details don't matter. For this particular example, if you do this, then the rate that you will obtain, how quickly the cost is decreasing to the optimal value, it will decrease geometrically of ratio 2/3, 0.66. Right, good. So this is somehow what an optimal constant step algorithm will do. Now let me do the following. Let me take two suboptimal methods. For instance, one with steps 1/5 and the other one with step 1/2. These are bad methods. One is very slow, the rate is very slow. The other one is diverges. Right? And my question is the following. Can I schedule these algorithms? Can I switch between them in some way? In such a way that this converges? Or let me be even more ambitious. Can I do this and obtain something that's better than this? Better than optimal? Right? It turns out in this case that if you're clever and you run these two algorithms in proportions, 2/3 and 1/3, if you mix them, if you want in these particular proportions, so think about taking one step with algorithm 1, one step with algorithm 1, then one step with algorithm 2, and you switch. In this case, you actually get a rate which is actually better, significantly better than the optimal constant step size. Right, it's better on both, and actually all performs, as I said, what you can do. So again, this is just an example. I'm not going to elaborate much more on this example. What I talk about mostly is the mathematics behind this. Parts of how do we start to understand these problems where we switch between different things, and the kind of unexpected things that happen, and what kind of computational tools one can bring to these kind of problems. Right, so what's a formal setting? It's usually called switch linear systems, which is exactly, I guess, what the name says. We want to have a finite set of matrices. A finite restriction is not really necessary, but I think it's a little bit simpler in that case. So we have some finite set of matrices, A1 to AM. These are square real matrices. And we consider it a linear dynamical system. X at my state at time k plus 1 is equal to some matrix times my previous state. And at every point in time, I choose one of the matrices in my set, which is the one that I'm going to apply. Right? So setup clear. Right? So it's kind of obvious if you expand this product, if you unroll the iteration, if you want, that understanding the system, the behavior of the system is really equivalent to understanding the behavior of these left infinite matrix products. Right? Somehow understanding whether this converges or what kind of properties it has is really trying to understand infinite products of matrices. Where, and again, that's a key difference, in here, perhaps I can choose at every point in time which matrix I'm going to apply. Right? So hopefully the basic setup is clear, but one of the things that it should be perhaps in your mind is, okay, you haven't really completely defined the problem, because who is picking, this, the sequence of indices, right? And there's different settings depending on, somehow what is going to happen. One setup, for instance, is a deterministic or worst case if you want setup. Or I want to ensure some property for all possible products that one can form, and there's no constraint whatsoever in kind of what sequences may appear. And I'm going to spend pretty much 2/3 of the talk talking about the situation. There's a very nice tool that we'll use to quantify somehow the convergence rate in this case, something called the joint spectral radius, and I'll define in just a few seconds. But also keep in mind that there's another situation, which is a random switching. Perhaps I have an explicit probability distribution between my indices 1 to m. In here, let's say that I pick them uniformly, and I want to understand the behavior of these random infinite products. Right? And for that, somehow the technical tools are something called Lyapunov exponents, which are a little bit different. And I'll also talk a little bit about this at the end. Furthermore, in both cases, we can really think about two different situations. One is the analysis question. The other one is a synthesis question. What do I mean by analysis? In the first case, a switching scheme is fixed. Somebody already chosen what they're going to do. And my task is simply to analyze this, to understand whether this converges or not, or to quantify the convergence. The other case is I'm the one actually deciding how to switch between my matrices. Think about, for instance, the example that I gave at the beginning. I'm supposed to find out that if I apply this algorithm 2/3 of the time, if I apply this algorithm 1/3 of the time, I do something better. So my task in that case is certainly more difficult, because not only I have to understand how it behaves, but I also have to come up with the policy. Right? So I'll mostly talk about the analysis situation, but I'll say a little bit about the synthesis case later. Good. So these kind of questions, of course, are not new. They go back, in particular, to the work of Roth and Strang in the 60s. So they define a very nice quantity, which I'm writing in here, called the joint spectral radius, which is exactly a quantification of how quickly the growth of these infinite products will be in the worst case situation. So let's unroll the definition. It's actually relatively simple. So what's happening in here, I'm looking at the norms of products of my matrices of length k. So I have in here the product of k arbitrary matrices. In here, I'm looking at the worst possible switching sequence. In there, I'm maximizing over these permutations. And then I take the kth root to normalize, and I take the lim sup when k goes to infinity. Right? So this is essentially trying to compute what's the worst possible gain that I can obtain in the limit when k gets very large in there. So as I said, this was defined by Roth and Strang in the 60s, and since then there's been a lot of work about different aspects of it. Why is it called the joint spectral radius? Because, of course, in the case of a single matrix, think about the situation where I have a single matrix in there. It's not very difficult to see. It's actually a nice theorem that what this definition gives you is exactly the spectral radius of your matrix. The spectral radius is the absolute value of the largest eigenvalue. Sorry, the largest absolute value of an eigenvalue of my matrix A. Right? Now, for the case of one matrix, this is wonderful. We all know how to compute kind of the spectral radius of a matrix. When we have two matrices, or more than two matrices, this is a lot more complicated. And this is really what this talk will be about. So, of course, here's some bad news. Trying to understand if this quantity is less than 1 or less than any constant is NP hard. I guess we expect this. Perhaps worse, particularly for this conference, this number is not actually a semi-algebraic function of the data. Kind of in general, we cannot expect to be the solution of some kind of polynomial that's a function of the data. Even worse, understanding whether this quantity is less or equal than 1 or less or equal than constant is actually undecidable. Right? And by this, what we mean is that there's no algorithm that kind of essentially can promise us that it's going to obtain the correct answer kind of as in every possible instance. Right? Think about things like the halting problem. Kind of essentially this can be reduced, or we can use a reduction to show that kind of this problem is kind of pretty difficult in that sense. Of course, it should not stop, and there's a lot of work kind of about these kind of things, both in terms of approximation properties and kind of some very interesting, for instance, algebraic combinatorics questions in terms of, for instance, is it true that if you have matrices, let's say 0, 1, 0, 1 matrices, is it true that a sequence that achieves this optimal value is periodic or not? Is eventually periodic or not? Or do we need non-periodic sequences? There's a lot of really interesting mathematics around it. What I'm focused today is really about questions about computation and approximation. Right? What can we compute this quantity? Can we produce algorithms that will give us approximations, nice approximations to this quantity? And in particular, also, if we want to produce examples. Remember my analysis question at the beginning, right? If I want to actually produce sequences that are bad, how can we try to do this? Good. So before I mention kind of the particular approach that I'll discuss, or the class of approaches that I'll discuss, let me make also an observation that without kind of changing things too much, we can extend the situation to the case of not of arbitrary switching, but the case where my switching is constrained by a graph, by a directed graph on an automaton. Right, so think about the situation where perhaps I have in here my 4 matrices, 1, 2, 3, and 4. And the way that I decide which matrix I will apply next is going to be constrained by where I am in this graph. So for instance, if at this particular point I'm at state Q3, the only matrix that I can apply in order to get out of this is going to be matrix number 1. If I'm in this state, I can apply either matrix 1, 2, or 4, and like this. So somehow I don't have the freedom of choosing my matrices arbitrarily, but they're constrained by some automaton. And we're going to see why somehow this setup, which slightly generalizes what I said before, is also quite natural. And this, I guess, motivates this definition of a constrained joint spectral radius. It's exactly what you'd expect. It's exactly the same definition, except that now my permutations are constrained. Sorry, my sequence is actually constrained to be a path in this graph. Right? Good. So how do we go about kind of trying to prove any kind of bounds on this quantity? So how do we do this in the case of a single matrix? In the case of a single matrix, kind of one of the typical ways that you try to prove some kind of stability or convergence properties of a linear differential equation is by trying to find a Lyapunov function. Right? You try to find some invariant, some function of the state that decreases along trajectories, and that's exactly what we're going to try to do. So let me state it formally in just a second, and we'll see how we can put this to use in an example. So here's a nice statement that, and this is where polynomials appear in this talk. Actually, they'll keep reappearing. So if we have, for instance, a polynomial P, which is strictly positive, a homogeneous polynomial of degree 2D, that satisfies an inequality of the following type. That whenever I apply P to the matrix A sub I x, this is always less than or equal than gamma to the 2D times P of x for all values of x in Rn. So essentially, it's an inequality between two polynomials, or between a polynomial and a shifted version of its polynomial. By shifted, I mean an affine transformation of this polynomial. But if I can actually find a P and some gamma for which this is true, then it follows that the spectral radius, the joint spectral radius of all the matrices A sub I is going to be less than or equal than gamma. Right? I'll show you the proof because it's a nice and simple proof. But is a statement clear? Right? In here, I'm asserting that if somehow one can find some number gamma and some polynomial P, for which these M inequalities are true, then you've actually succeeded in proving an upper bound on your joint spectral radius. So how does this work? So the proof is actually quite simple. So first of all, let me make the observation that if P, my polynomial, it's a homogeneous polynomial, is strictly positive, then I can upper and lower bound it with multiples of the powers of the variables. Right, this is essentially because on the sphere, it will achieve its maximum and its minimum. The minimum is going to be greater or equal than 0. So that's why we have these inequalities. And then once we know that, we can start bounding the norm of any infinite sequence of products, any finite sequence of products, right? Because if I want to bound the norm of this product of matrices, this is, if I use an induced norm, this norm is less than or equal than the maximum over vectors of this ratio. And now I can use this inequality to bound both the numerator and the numerator by replacing norms with this polynomial P. Right, so essentially I can replace in here with P applied to this sequence of matrices. I do the same thing in the numerator, and I have a factor that really will depend on the ratio between alpha and beta. And now once I have this, I can start peeling out the factors, the matrices, one at a time, using this inequality. And every time you peel one of the matrices A sub I, you get a factor of gamma that appears in there. Right? So after peeling your k copies of your matrices, you get something like this. So now in this inequality, remember in the definition we have to take roots 1 over k and take the limit. So essentially this constant will go away, and what we end up getting is exactly that this is going to be bounded by gamma. Right? So what have we done in here? We've said, okay, this difficult question of trying to bound this convergence rate under arbitrary products, now we can obtain this kind of, in principle, sufficient characterization by finding some auxiliary polynomial that satisfies kind of a whole bunch of inequalities. Of course, it should not be terribly, and by the way, what's a physical interpretation, if you want, of this? Think of P as some kind of proxy for the energy of the system. Right, and what this is telling us, what this inequality is telling us, is that the energy decreases by a factor of gamma every time that you apply one of the matrices A sub I. So if this is going to be true every time that you apply a linear map A sub I, then kind of you're essentially proving what you want. Now, okay, great theorem, but this is not very actionable. How do we find the polynomial P that satisfies kind of these kind of weird inequalities? And in fact, I'm even cheating in here, because even verifying these inequalities is actually NP hard. We cannot verify polynomial inequalities, even if somebody comes and gives me a P. Kind of we cannot check efficiently that this inequality actually holds for any P. So what's the idea? Somehow we want to really replace these positivity inequalities, P being positive, and the difference between this polynomial, taking this to the other side, being positive, by sum of squares conditions. That really means that this polynomial, I can write as a sum of squares of some other polynomials, and the same thing is going to be true in this side. And of course, this is a weaker condition, or a stronger condition, because if my polynomial is sum of squares, certainly it will be positive, but this is still going to be sufficient to verify what I want. Now, the beauty of it, the positive aspect of it, is that once you replace positivity with sum of squares, something that was a pretty difficult, a computationally difficult condition, now becomes something that we can efficiently do in terms of convex optimization. And the reason is because we can really re-encode this in terms of semi-definite programming. So once we get to this point, this is something that you can actually take in your computer and compute polynomials P, and we'll do this in just a second. Let me also make the observation that, of course, in here, even in my theorem over here, somehow the degree of the polynomial is a parameter. And as you would expect, if you allow the degree of my polynomial to be larger and larger, I have a lot more freedom in terms of what polynomials P I can choose. And we would expect, and in fact it's true, that gamma will actually increase. Gamma will decrease. And my bounds are going to get better and better. Right, so let me give just an example so it's clear. What happens is a well-known example in this field. Take these two matrices. These are two 2x2 matrices. It turns out that if you apply any arbitrary products of this, then the norm, or the joint spectral radius, is going to be 1. It's exactly bounded by 1. But if you try to use, for instance, any quadratic function to prove this, any quadratic polynomial, the best bound that you will obtain is something like square root of 2. On the other hand, if you take kind of the formulation that I used before, you can show that this polynomial P, for instance, so epsilon in here is some arbitrary parameter, epsilon is positive. So this is a quartic polynomial in here. And if you form these differences, P of x minus P of A1, you can also see that these differences are actually themselves sum of squares, they're actually even squares. So what this proves is a bound of 1 plus epsilon for every epsilon. So it's exactly proving that the joint spectral radius of this is equal to 1. And what I'm drawing in here are the level sets of this polynomial. Right, so this is an example, for instance, where we can actually certify that this upper bound, an upper bound of 1, or 1 plus epsilon if you want for every epsilon, by explicitly showing a polynomial, and in this particular case, it's actually tight. Right? Good. So what is a natural question that one may think about in here? Okay, fine, you propose some method for upper bounds. How do you know that it doesn't get stuck? right? That if you don't prove a bound of 100 when the true value is 2, or something like this, or even more. Can you say anything at all about the approximation properties? About if I want an approximation, an epsilon approximation, then what degree of polynomial should I use in here? And I think the other thing that you should keep in mind is somehow that seems to contradict perhaps some of the things that I talked about this being hard to approximate, undecidable even to compute. Right? So here's a nice statement that you can show about the quality of this bound. If I'm trying to produce this upper bound, which I'm calling rho SOS to D, on my joint spectral radius rho, then what we get is essentially that I'm sandwiching rho between the value that I computed and the value that I computed times some constant. And that constant essentially depends on the degree of the polynomial that I use, m, which is the number of variables, n, which is the cardinality of the state. Right? And one of the things that's easy to observe is that when you take the degree go to infinity, if I allow polynomials of higher and higher degree, then this approximation ratio goes to 1. So this is actually computing an arbitrarily good approximation to the optimal value that you want. And this does not contradict the undecidability of actually understanding whether this number is less or equal than some particular number. The reasons are not very difficult to understand, but let me not expand on this. Right? So again, and somehow the nature of this bound, there's kind of really two bounds. One, if the one that depends really on the number of matrices, and kind of also a bound that depends somehow on the dimension of a state. So this is great. Kind of what this is telling us is, look, if you have this particular problem, you can use convex optimization and semi-definite programming to produce an upper bound on this value and with some guarantees. The converse question or the associated question is, can you use somehow this technology to produce high growth sequences, to produce a sequence of matrices in there that kind of is also close to optimal? Right, and of course, a general philosophy, I mean, something that perhaps you may want to keep in mind for other problems, is that if at any point you're using some methods based on convex optimization to prove something, then the dual of this convex optimization problem should somehow also give you useful information that you can use for whatever problem you want. So somehow, in my situation, a natural question is, if I told you that kind of we were going to try to produce bounds by solving this convex sum of squares or semi-definite programming or convex optimization problem, how do we use the dual of this to actually produce interesting sequences? And the answer is we're going to be able to do this. In order to describe this in just one slide, let me remind you the constraint setup, because it's kind of easier to explain just in the constraint situation. In here, and the only difference, if we want to adapt the method that I described before to the constraint situation, is that we'll have the same kind of inequalities. But now it will make sense to have polynomials in here that are local, that actually depend on which node you are. So before, we were just using one polynomial p for the whole system. Now it kind of makes sense to use one polynomial p for every state that you may be in. And we're going to see why that appears. But otherwise, the proof that this is enough is exactly the same, because every time that you pull one of the factors, you're really only using it on the corresponding polynomial. So this is the sum of squares program that we would write for the constraint case. Just like before, we're trying to find polynomials that are sum of squares, that they satisfy certain inequalities between pairs of polynomials u and v, or pairs of nodes u and v, whenever I apply transition sigma. And the natural question is, what is the dual optimization problem of this, and how do we use this dual to generate any kind of sequence? So duals of sum of squares, they have some very nice interpretations in terms of essentially what's called pseudo expectations. So what's a pseudo expectation? What's an expectation? It's really a linear map on a function. You give it a function and it returns a number. So what's a pseudo expectation? It's a linear map that takes polynomials and will give you a number. But these polynomials, these pseudo expectations, are only defined on polynomials of low degree. I cannot apply a pseudo expectation to a polynomial of high degree. To what degree I can apply it exactly to the polynomial, to the degree d for which I compute my program. And in this case, for instance, kind of when you write what the dual constraints look like, again, the notation is not great, but kind of it will look like some inequalities of this type. What is the only thing that matters for, in the context of this talk about these inequalities? That what these inequalities are really saying is that there's some kind of inequality between the incoming and outgoing flows in every node. So when I look at node B, for instance, in here, what this inequality tells me, which I'm writing explicitly in here, is that when I sum the expectation of the incoming polynomials, that has to be greater or equal than some constant times the expectation of the outgoing polynomials. Think about the conservation of flow type condition. Right? So essentially, any time that the dual program is feasible, that means every time that there is a sequence that achieves a certain cost, then an inequality of this type is going to be true. Now, if I want to somehow distill from this an actual sequence, what I have to do is somehow replace these expectations or by somehow a particular trajectory. And the way that we'll do this is essentially something like dynamic programming. We're going to look in here, or we want to explicitly construct an infinite sequence backwards using a best expectation by lower bounding the maximum of the average. So essentially in here, if you've ever seen any kind of rounding method, like, this is exactly what's kind of going on in here. You know that something is promised to you because of an expectation inequality, and then you know that that exists at least one value that achieves that, and that's exactly what they're doing in here. I mean, this is telling us, if you build the sequence backwards, that the average of this achieves a certain value. So in particular, there has to be one of them that achieves that value up to a certain constant, and that's exactly what they use to probe the existence of this sequence. So again, at the high level, what's happening in here, we probe upper bounds by solving this convex optimization problem, and the dual of this convex optimization problem gives you a way of constructing these sequences. Right? Good. So, and why do we care about this? Because again, in most of these situations, not only you want to ensure that you have some bounds and performance on how this is switching, but you actually want a particular policy and some explicit policy in there for how to switch. So before switching to that wasn't a pun, before changing to the random case, let me describe briefly a particular situation which is very nice, and one can actually analyze it very explicitly. And I think also it will highlight a little bit the differences between this particular case and with the general situation. And it's a case of rank 1 matrices, right? So what happens in here when all your matrices in there are rank 1? And what kind of makes it very, so this has also a nice geometric interpretation. So for instance, if my matrices are symmetric, so imagine the situation where all my matrices are symmetric of the form U sub I transpose, then what is a geometric interpretation in here of applying one of these linear maps A sub I at every point? If you think about it, what you're really doing is you have a set of lines in space. These are the U sub I's, the lines spanned by the vectors U sub I's. And what you're doing is at every step, you're choosing one of the lines, and you're projecting into that line and possibly scaling with some factor. So the question of this convergence of arbitrary switching, or detecting whether the joint spectral radius is less than 1, is exactly the question that if I project over these lines in some arbitrary sequence, whether this will eventually get to 0 or not. And again, it's not just projection, it's projection and scaling, possibly, with some factor. Right now, what makes this rank 1 case particularly nice, and actually even in this case is kind of non-trivial, is that in this case we can actually reduce this to a nice combinatorial problem on a graph. Right, so in this case, remember my matrices are of the form U sub I, V sub I transpose, so I can construct some graph in there where the nodes are my matrices in there, and the weights of this graph are, we can label, let's say, by the log of the absolute value of the product between those. The idea being that somehow if product of these matrices A sub I will correspond to a particular path of the graph. And you can see where the rank 1 assumption matters, right? Because when you multiply two rank 1 matrices, you can take the factor in the middle and pull it out, right? when you multiply a matrix of the form U sub I, V sub I transpose, with a matrix U sub J, V sub J transpose, then the inner factor is a scalar, and you can just pull it out. So somehow the rank 1 situation is very special, because in this case, somehow there's really no state that affects the future. Somehow the only thing that matters is really where you currently are. Let me make a bad analogy. It's like a Markov process, right? The only thing that matters is what's the state at the current time. So what happens in this case? Somehow finding a good switching sequence is equivalent to finding a good cycle on this graph. What does it mean to find a good cycle? It means to find a cycle with what's called the maximum cycle mean. If I have a directed cycle, I can compute the average weight of that cycle, and my task is to find the cycle of this graph that has a maximum average weight. It's kind of well known since, 30 years ago, 40 years ago, that this problem can be solved efficiently using dynamic programming. So in particular, in this case, this gives some nice algorithm to solve exactly the rank 1 situation. But this doesn't extend, none of this extends to the case of certainly higher ranks. And actually, one question that is open is what's the smallest rank for which a problem actually becomes undecidable. It's unclear, for instance, if there's any kind of nice algorithm for the rank 2 case, or even approximation questions in this situation. Good. So let me move on or say a few things about random switching. So what happens in the random situation, like I said before? So now we have, again, my finite set of matrices, and I have some explicit probability distribution P sub I over these matrices. Again, think about the uniform distribution. And what I'm doing is I'm switching independently between the matrices according to this probability distribution P sub I. Right? So just in the same way, we can define in a very natural way the growth or the rate, if you want, of this under this random switching situation. And this is exactly given for a particular switching sequence by this quantity Rp of sigma, again, for a fixed permutation, which is a limit, just like before, of the kth power, of the 1 over kth power of the norm of the products. Right? So it turns out that this quantity in here concentrates. So essentially, if you pick a sequence of large length, then the value of this quantity is pretty much going to be independent of everything. It will not really depend on which particular sequence you are. And in fact, there's a very classical characterization of this by Furstenberg and Kesten in terms of what's called the Lyapunov exponent, which is defined, and again, the definition looks similar, but it's not exactly the same thing, where you're looking here at the expected value of the log of the product of matrices, and then you normalize and you take the limit. So the difference, notice, between this and this is now in here, this is given for a simple, for a given sequence. In here, we're taking expectation of the log of the product of these norms. And one of the things that what this theorem does is gives an alternative characterization of this in terms of an expectation over an invariant measure, right? But that's not really useful from the computational point of view, because most of the time we don't know what the invariant measure is, and we don't have access to this invariant measure directly. And there's a lot of applications of this, particularly in ergodic theory, and again, stochastic kind of systems in general. So the random case is also it's as complicated, if you want, or perhaps in some sense even more complicated than the deterministic case. But the kind of questions that one would like to ask, they're exactly of the same kind, right? One would like to understand, for instance, can you compute some kind of bound on these Lyapunov exponents? Can you compute some kind of bounds on the convergence rate? And just because I guess it's expected, and it's actually true, even deciding stability, deciding any kind of property about this will suffer the same kind of algorithmic undecidability that happens in the general case. But that doesn't, of course, say that one cannot try to produce bounds, or one cannot produce bounds with certain provable properties. And recently there's a very nice convex bound, for instance, if you want a little bit of an analog of the bounds that I described before in terms of semi-definite programming for this Lyapunov exponent case, in terms of some nice optimization problem that involves some kind of entropy-like quantities. But I think one of the things that we don't quite know is how well we can approximate, what kind of approximation properties we can get for these kind of problems. Going back to the question that I had at the beginning, we may also be interested in this design question, right? So again, imagine the situation where I have this fixed set of matrices, and my task now is, can I find the probability distribution over my matrices in such a way that if I switch according to this distribution, somehow something nice happens? And one of the things that we've shown recently, and actually I'll talk about this in just a second, is that even that this problem, of course, as you would expect, is also pretty difficult. Right? In particular, we cannot even decide efficiently the question of can you find the probability distribution for which this spectral radius or this Lyapunov exponent achieves a certain value, even in the rank 1 case. Even in the rank 1 case that I talked about before, although in some sense it's still kind of, although it's NP-hard, it may have some nice approximation properties, and I'll tell you in just a second what it is. And this is kind of interesting, because in the rank 1 case, like we've seen, the deterministic situation is actually quite simple. If you ask me, come up with a policy for switching, a deterministic policy for switching between these matrices, it's actually very explicit. We get exactly a particular cycle, and we can just kind of write it down and solve it in polynomial time. But if you ask me, can you find probabilities? And then I'm going to switch in some IID way, then this is already a hard problem. So it's a kind of interesting contrast of the deterministic versus a random situation. So what happens in the rank 1 case? The problem still simplifies in some nice way. So now what happens is that instead of solving this maximum mean cycle problem, what we have is some nice quadratic optimization problem over the simplex. So the problem that you have to solve is this matrix, if you want, this is really square matrix, which is the adjacency matrix of the graph that I described before. And now what you're trying to do is really to try to minimize this quadratic form over the unit simplex, where P is in the unit simplex. So the minimizer of this is going to be some vector P in the unit simplex, some non-negative vector that adds up to 1. And that's exactly going to give us the optimal distribution to switch among these variables. Right. And as I said, it follows from the inapproximability properties of independent set that the design question, the finding this P, is actually a difficult problem that comes exactly because minimizing quadratic forms over the simplex, is it's a difficult problem. Although there are certain nice approximation results that we can use in this case. So what is the bottom line, if you want, of this? And I'm pretty. I guess I went a little bit quicker than I expected. So the bottom line in here is that if we have a deterministic situation, we have a random situation. The tools that one can use to analyze the deterministic case and the random case, they can be quite similar in the sense that they're based on convex optimization methods. And one thing that keeps appearing again and again is that this possibility of once you prove any kind of upper bound using optimization methods, to use duals to actually produce either sequences or explicit probabilities that will have somehow the properties that you want. As I said, I'm finishing early, so I guess you'll be happy. Switching is a very powerful algorithmic tool. It's quite counterintuitive. It's quite easy to, I guess, get confused in terms of what you can or cannot expect in this kind of switching situations. So one of the things, if you want, that happens, as I highlighted before, is that even in the very well-studied situation of even in the very natural situation of having a process which is homogeneous in time, then the optimal solution will actually break this time symmetry. So for instance, again, think about in the case of optimization that I was talking about at the beginning, once I allow myself for the possibility of switching between my two algorithms, I can actually get something that's better than any of them. The techniques, again, they branch out whether you look at the deterministic of the random case. But I think there's enough commonalities between them that I think it makes a lot of sense to think about jointly. As I said, there's a lot of open questions in terms of the behavior of this. Some I think a very interesting question is what kind of conditions can one impose on these matrices in such a way that this quantity, the joint spectral radius, is actually an algebraic function or semi-algebraic function of the data. We certainly know situations where it's not. In the rank 1 case, for instance, it is. But kind of other additional situations for where this happens. If they form some particular semi-group for nice properties, there's some nice results, for instance, about the when the matrices form some kind of Lie group of a certain type. But I think in the general case, we don't have a very good understanding of this. So here's some references if you want, and thank you for your attention.
Thank you very much. Is this on? I think so. Okay. Are there any questions? We have plenty of time today.
And a throwable microphone.
Yes.
I think Maurice's question.
Marcy? Yeah.
There's a question.
Can you say something about the convex formulation of the bounds for the Lyapunov exponent?
For the Lyapunov exponent?
For the Lyapunov, yes.
So that's in this paper by Suter, Fauci, and Renner. And what they do is essentially it's a nice optimization problem where you optimize over matrices of trace 1, again, positive semi-definite matrix of trace 1, and the cost function is essentially like like a relative entropy type thing. So you minimize like the log of the trace of, like the inner product of this unknown matrix X and all your generators A sub I.
Thank you.
Other questions? I don't see anyone.
You can catch.
So in your SOS problem, do you have any knowledge of the degree you will have to attain for the polynomials to have
so this will tell you from this expression, you can actually back out if I want an epsilon approximation, of what degree I want.
You have explicit...
So it is explicit dependence, right? So as a function of the parameters, M, N, and D, you can compute this number. The approximation factor that you want, the relative approximation factor, is this. So once you know that I want a precision, 0.9, 0.99, whatever, then that allows you to compute the D that will satisfy this. By the way, I should mention, these bounds are, and this is common actually of many, many things about polynomial optimization and things like this. They're quite conservative in the sense that for most problems, most of the time, at least in the dimensions of which we can actually compute things, we actually get much better results. So for instance, think about the example that I was doing in here, right? For this particular case, degree 4 allows me to compute this all the way to the optimum, right?
It's another one back there.
Where?
Peter. No, more questions.
Okay. Are you familiar with Motzkin's method for solving linear systems?
Yeah.
Is there any relationship between these random projection methods and...
No, so more than Motzkin, I think this reminds probably many people to Kaczmarz, right? So in the Kaczmarz method, what you have is a set of linear equations, right? Or the geometric version, if you want, of Motzkin, is that you have a whole bunch of hyperplanes. And what happens is at every point you project onto a hyperplane. Now, the hyperplane situation is not rank 1, but it's actually rank n minus 1. And what happens in that case is essentially that things don't work, right? Because so somehow it looks similar because it's also somehow the convergence properties in there, they're also determined by the arrangement of these lines P sub I, or the normals to the hyperplanes, but somehow it's exactly the rank n minus 1 situation, not the rank 1 case. And it's not very clear if anything is particular, if there's anything special about that case. Yeah.
Peter, can you throw it back?
Thank you. Okay. I'm a bit puzzled about this undecidability result by Blondel and Tsitsiklis. And then you have the other result using SOS. So I think the reason must be, of course, that you use SOS instead of the cone of positive polynomials. But then we know, I mean, by Tarski, etc., deciding positivity of polynomials is decidable. So still, the other problem you study is undecidable. So I'm a bit puzzled about what's
so
going
it's really
on
a
there.
difference between the strict versus non-strict
Yeah.
inequality. So essentially, so for instance, if you're asking here whether this is less than or equal than 1, if you could say that if it's less than or equal than 1, it's less than or equal than 1 plus some quantity that you can actually computably bound, then, you know, kind of somehow there would be a contradiction. But what happens in here is that, you know, kind of this may be less than or equal than 1, but I may not be able to bound in any computable way how much smaller than 1 it is. So it may, so essentially what this kind of method will tell you, right, is that if you give me any epsilon in here, where am I? If you give me any epsilon in here, I can compute some d for which this is guaranteed to be true. But the point is, given the problem data, I cannot tell you what epsilon I need in order to understand whether this is less than or equal than 1.
Okay.
Is it me?
I'm not sure I understand, but okay. So,
So, can you turn your microphone face away from you, I think, or no, away from me. I think.
okay. Acoustic feedback.
So let me try to say that perhaps in a different way.
No, I was just very theoretically, if I would just, you know, I'm just hunting for decidability, I don't care about complexity. And then I would answer this question about positivity using any crazy algorithm.
Yeah.
But still, it cannot give this result.
No, because in here I'm talking about the true spectral radius. Right? This is about the true joint spectral radius.
Yes.
What Tarski-Heidenberg will allow you to tell you is whether the bound of degree V is less than or equal than some quantity.
I see.
Right?
Okay.
So these are different things.
Okay. 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 Thank you.
Okay, maybe there's time for one more question. Back, just behind you, Peter.
That's easy.
Thanks. So just a question, is there any hope that SOS bounds could be tight? Could you have sometimes finite convergence, or is there a reason why it could not happen?
Well, in some cases it does.
Or it can happen?
Yeah. Like, for instance, I mean, okay, this is a bad example. Think about the case of a single matrix, right? For a single matrix, like, you know, kind of, then essentially, and the same thing is true if the matrices, for instance, are very close to each other. So there are certainly data for which, you know, kind of, you get finite convergence, but there's also examples, like exactly this one, where you don't get finite convergence in the sense that you get 1 plus epsilon for every epsilon. And this is true for all degrees. It's not true just for 4.
Okay. Do you want to say something? Sure. Okay. So Jan's going to, should we thank him first? Okay. All right. Let's thank Pablo again.